In this video, we're going to explore specific heat capacity. Specific heat capacity is the first real big concept that we come to when studying thermochemistry. The definition of specific heat capacity is it is the amount of heat that is required to raise the temperature of 1 gram of a substance by 1 Kelvin. Kelvin is a unit of temperature that we'll be exploring in much more detail in later units. For now, we're just going to recognize that Kelvin is equal to our degrees Celsius plus 273.15. When we talk about temperature in this unit, much of the time we're going to be talking about temperature changes, which we would write as delta T. Delta being a Greek symbol that typically just stands for change, and so delta T is our change in temperature. Since Kelvin is just equal to our degrees Celsius plus 273.15, a delta T of 1 Kelvin is also equal to 1 degree Celsius. And for that reason, since those changes are equal, you will quite often see Kelvin and degrees Celsius used interchangeably when discussing these energy terms. Now back to specific heat capacity. The specific heat capacity is a property that does depend on the amount of the substance we have, the size of our temperature change, and also the identity of the material. Here we see a chart of the specific heat capacity of some fairly common materials. Since specific heat capacity is the amount of energy required in order to change the temperature of a substance, what that means is that substances with a higher specific heat capacity resist temperature changes more so than substances with lower specific heats. For instance, something like glass, with its very low specific heat, is very easy to heat up, as opposed to aluminum, with a much higher specific heat, requires more energy to raise the temperature by the same amount. If we compare the specific heat of water to surrounding land, water has a higher specific heat capacity. This is the reason that coastal climates typically will be more moderate in temperatures. The water helps to keep the temperature more constant due to its higher specific heat. To calculate specific heat, we use the equation Q will equal C times M times delta T, in which Q is going to equal our energy gained or lost as heat, M equals our mass of the substance, and delta T equals our temperature change. To find our change in temperature, we simply take the final temperature and subtract the initial temperature. And we'll just note here that depending on what source you're looking at, you might see some of these variables written in a different order, but it's still the same equation. For instance, you might see Q equals MC delta T. That's the way that I quite often write it, simply because that's the order that I learned when I first learned specific heat. But it's the same exact equation. Let's take a look at an example of a calculation. So here, we want to find what quantity of heat has been transferred in order to heat 50 grams of water from 25.3 degrees C to 33.7 degrees C. And so we're going to use our specific heat equation, Q equals MC delta T. We know our mass at 50.0 grams. We are given our specific heat, 4.184 joules per gram per Kelvin. We can easily calculate our change in temperature. Our delta T is going to equal our final temperature, 33.7 degrees C, minus our initial temperature of 25.3 degrees C, for a temperature change of 8.4. We multiply these together, and we get a value of 1.76 times 10 to the third joules. It's quite often convenient for us to think in terms of kilojoules because quite often we're dealing with large amounts of energy, and so we might convert this to 1.76 kilojoules. In this example, we want to calculate the heat required in order to warm approximately 1 cup of water from about room temperature up to near the boiling point. And so we're going to use our same equation, our Q equals mc delta T. We're given the exact mass of 250.0 grams. Our C is the same, it's still water, 4.184 joules per gram degree C. And again, we know our temperature change. Our delta T, our final temperature is 98. Our initial temperature was 22. For delta T equal to 76 degrees C. For a final value of 7.95 times 10 to the 4th joules, or 79.5 kilojoules. If we know the heat and we know our temperature change, we can also calculate the specific heat given a specific mass of a metal. In this case, we know the amount of heat that it took in order to raise the temperature of a sample of silicone by 6 degrees, and we want to find the specific heat. So our equation is the same, our Q equals mc delta T, but now we want to be able to solve for our specific heat. And so I always find it easier to rewrite my equations first, and so we're going to solve this equation for C. And so C equals Q divided by our mass times our temperature change. And so now we can just plug those values in. We were given Q, a heat value of 192 joules, and we will then divide that by our mass of 45 grams times our temperature change of 6.0 degrees C for a final specific heat of 0.71 joules per gram degree C. Similar to density that we studied earlier, specific heat capacity is an intensive property. Thus, it's a property of materials that does not change no matter how much we have. Therefore, it's something that can be measured experimentally. And so let's take a look at how we might do that. Let's imagine that we have a sample of metal that we heat up. In this case, we've got 55 grams of iron. We heat that up to 99.8 degrees C, and then we're going to drop that into a sample of water at 21 degrees C. And so we can imagine what's going to happen if we let the metal sit in there. The metal is going to cool down, and the water is going to heat up. And so our delta T of the metal is going to be negative. Therefore, our Q will be negative, because remember, Q is just equal to mc delta T. And if we look at it from the point of view of water, the delta T of water will be positive because it's going to heat up. Therefore, the Q, the heat from water, is positive. Thinking about this another way, if we're thinking about this from the terms of the metal, Q is negative because the metal is losing energy. The metal is cooling down. Whereas the water, Q will be positive because the water is gaining energy. And so if we think in terms of our entire system, the law of conservation of energy tells us that the energy in any system will be conserved. Therefore, the total amounts of energies involved in a total system will equal 0. And so if we apply that to this situation, we know that the heat associated with the metal plus our heat associated with the water will equal 0. Another way to think about that is that since we know the heat from the metal was negative, and our heat from the water, and so the heat lost by the metal is going to be exactly equal to the heat gained by the water. This is the key relationship that we need in order to be able to calculate the specific heat of a metal. The heat lost by the metal as it cools down will be exactly equal to the heat gained by the water as it warms up. And so experimentally, what we can do is heat a sample of metal in boiling water. That's helpful for us because we know the temperature at which water boils. And so if we leave the metal in there long enough, we know the temperature of the metal will be 100 degrees C. And then we can drop that metal into the water, and we know that the heat lost by the metal is going to equal the heat gained by the water. And we can set up an equation in order to look at that. So our heat lost equals our specific heat of the metal times the mass of the metal times the delta T of the metal will be equal to the heat gained by the water, which is equal to our specific heat of the water times the mass of the water times the temperature change of the water. And so let's write that out in even a little bit more detail. And so our specific heat of the metal times our mass of the metal times our delta T of the metal will equal our specific heat of the water times the mass of the water times the delta T of the water. Now these are all quantities that we will be able to either measure or that we know. So let's look at an example. Here we have a 145 gram sample of copper. We boiled it in water for a while, so it's at 100 degrees Celsius, and we place that into 250 grams of water, which is at 25 degrees C. We let the temperature reach an equilibrium, and at that point the temperature of our water is at 28.8 degrees Celsius, and we want to calculate the specific heat of the copper. And so, again, we can set up our relationship in which we know that our heat lost by the metal is going to equal our heat gained by the water. Our heat lost by the metal equals the mass of the metal times the specific heat of the metal times our temperature change of the metal. Our heat gained by the water equals the mass of water times the specific heat of water times the temperature change of our water. And then we can set those two quantities equal to each other because we know the heat lost equals our heat gained. We do that and we get the mass of the metal times specific heat of the metal times the temperature change of the metal will equal the mass of the water times specific heat of the water times delta T of the water. And so here's our equation that we developed before. Now we're trying to solve for our specific heat of the metal here. And so what we can do is we can just solve this equation for that specific heat of the metal. If we divide both sides by the mass of the metal and our temperature change of the metal, that will equal for us the specific heat of our metal. And so now we're ready to just plug in our values. We know the mass of the water is 250 grams. Specific heat of the water, 4.184 joules per gram degree C. The temperature of our water went from 25 degrees Celsius to 28.8 degrees Celsius for a temperature change of 3.8 degrees C. We were given the mass of the metal at 145 grams. Our metal went from a temperature of 100 degrees C to 28.8 degrees C for a temperature change of 71.2 degrees C. We plug those into our calculator and we get the specific heat of copper to be 0.385 joules per gram degree C. In this example, we're doing the same thing with a piece of iron in which we know its specific heat, but now we want to calculate its mass. And so we go through the same exact process we did before, where our heat lost by the metal is going to equal our heat gained by the water. And so we set up an equation just like we did before. Only now we want to solve for the mass of our metal. And so to do that, we divide both sides by the specific heat of the metal and the delta T of our metal, and that's going to equal the mass of our metal for us. And so now we can plug in the numbers. And then plugging them in, calculating, gives us a mass of iron of 57.4 grams. And so the key takeaways from this video are that specific heat, C, is equal to the energy required to raise 1 gram of a substance by 1 degree Celsius. In order to calculate the energy involved in a temperature change, Q will equal our mass of our substance times the specific heat of the substance times the temperature change. Finally, we want to recognize that if we are putting two materials of different temperatures together, the heat lost by the material that's cooling down will equal the heat gained by the material that's warming up. The law of conservation of energy tells us that has to be the case. And so in this video, we explored several of the concepts related to specific heat capacities. If you are looking for more assistance, feel free to look at some of the examples on the website or come see me for some help. I hope this has been helpful.